Good noon, everyone, and welcome to this week's Keeping Current. It's good to have you here. I'm hoping there'll be more people joining us, but we will start in any case because I like to start on time. Today we have two talks, and the first is Nathaniel Hudson, who will be telling us about some work he's been doing with Professor Hamfrush about maximal clicks in online social networks. Of course, I never click. So anyway, take it away, Nathaniel.
Okay.
And feel free to share your screen.
Yes. All right. Hello. So my name is Nathaniel Hudson, as Dr. Finkel introduced me, and this is my work entitled Smart Advertisement for Maximal Clicks in Online Social Networks Without User Data. This paper has been accepted to the Smart Comp 2020 conference, where I will be presenting it next week. And yeah, so without further ado, let's get started. So at first, I kind of want to talk a little bit about the motivation for this work. As we all know, social media platforms, particularly online social media platforms like Facebook, Twitter, Twitch, etc., have become increasingly prominent ways for people to consume information and even essentially acquire information related to current events. And it goes without saying that there are some information that are much more time sensitive. They might be related to a very critical problem that we need to make sure that people respond to and they get the information. An example of that would be a natural disaster, or if you can imagine such a thing, a global pandemic. So with that in mind, we need to be able to make sure that we are able to reach people with crucial information as optimally as possible. However, if you look at the related works, this is not an new problem. Most of these online social networking platforms such as Facebook, Twitter, etc., have already devoted a great deal of time and effort in research and development to try to find optimal ways to maximize click-through rate, which is the formal term with regard to clicks on online social network platforms. However, conventional approaches are very user-centric. Typically, they will model the problem as being a binary classification where you consider a user and you try to classify whether or not a user is going to click an ad or not, and you summarize that over a large population of people. And essentially, those binary decisions on whether or not a user is going to click an advertisement or not, that is going to be based on their demographic data, their geolocation data, and a bunch of other information about them that people may be less privy to actually having be visible to advertisers. And because of growing concerns for privacy, we aim to try to approach CTR optimization and prediction without having any access to user data in any capacity. So that's kind of the focus of this work, and that's what sets it apart from more conventional approaches to CTR optimization in the literature. So a high-level overview of our methodology. First, we have to start with the data. And the data that we use is actually a very interesting treasure trove of data that was released by the United States Congress in 2018. We refer to it as the IRA data, but essentially these data is a collection of advertisements that were bought by Russians before, during, and after the 2016 presidential election cycle. So it's quite interesting to kind of go through all of the data. But we use this because there's a lot of different features that can be used in order to come up with models in order to perform prediction. Secondly, we incorporate natural language processing, or NLP, in order to essentially categorize advertisement targeted interests, which we'll talk a little bit more later about, but we try to categorize them into what we call conceptual nodes. The reason for this is just because the amount of targeted interests that are in the data are just too vast to really extract meaningful information from. And secondly, we try to study optimal ways of allocating conceptual node combinations using machine learning in order to try to find ways to predict click values given a CTR combination, and also to allocate optimal combinations of conceptual nodes. Finally, once we have trained machine learning models to perform click-through rate prediction, we then propose a greedy and a genetic algorithm in order to find optimal conceptual node combinations to find maximal click-through rate. So let's start with kind of going over what these Facebook advertisements look like. So to the right, you can kind of see, and you get an idea of what these data look like. There's a PDF document for each advertisement with a picture of what the advertisement looked like, and then some more raw features pertaining to the advertisement. Some of these features include number of clicks, number of impressions, which essentially means how many people have viewed the advertisement, the amount of Russian rubles that were spent on trying to promote the advertisement, when the advertisement began to be displayed on Facebook, when it was taken off Facebook, and most importantly, in my opinion, the targeted interests that were selected when they were trying to target the audience for this advertisement. So with that said, the features that were found across all of these advertisements were not consistent, they were not standard. So a lot of pre-processing power had to go into this phase of the work to try to make sure that we, one, had a consistent body of features that were being extracted from these data. And what we found were that there were essentially 5 key features that were consistently found across all of the data. Number of clicks, spend, start date, end date, and targeted interest. And targeted interests, as I mentioned earlier, are probably the most crucial of this entire process, because these are the features that we're going to then essentially categorize into what we call conceptual nodes. So what is a conceptual node? So like I said earlier, a conceptual node is essentially a thematic category to essentially try to organize all of these targeted interests into distinct groups that kind of just summarize essentially like a genre for each of the targeted interests. And the reason for this is just, like I said, targeted interests are very vast. There's a lot of them. Some of them are almost redundant for interests. One of the targeted interests would be African-American culture and then African-American music. So we kind of want to iron out that redundancy so that way there's not overfitting of our machine learning models or any other problems, and that the machine learning models, once they're trained, can be useful. So the way that we perform this conceptualization via conceptual nodes is we use NLP classifiers that were developed by Facebook, known as the fast text model. If you're not familiar with the fast text model, the fast text model is essentially an extension of the famous word-to-vec model, except the fast text model, if it sees a word that is not within its vocabulary, it will break it up into n-grams instead, so that way it's more flexible and less error-prone. So essentially what we do is we train a fast text model for each of our conceptual nodes that we're considering, and then each of these fast text models can then provide a similarity score for a conceptual node that it is provided, and whichever conceptual node's fast text model provides the highest similarity score, we essentially assign that targeted interest to that conceptual node. So that's how the mapping takes place in this phase of the project. For our work, through a lot of experimentation and just reading through a lot of the data, the 6 conceptual nodes that we kind of settled on were celebrity, identity, news, religion, organization, and politics. And now I want to kind of go into the overall process of how these all kind of play into one another, how we extracted the data necessary in order to train the fast text models for each of these conceptual nodes, and the evaluation phase as well. So first, we consider 4 different predictive regressor model types: AdaBoost regressor, decision tree regressor, multi-layer perceptron neural network regressor, and random forest regressor. So we're wanting to train these 4 model types at the end of the day. However, in order to do that, we first need to train those fast text models for our conceptual nodes. And in order to do that, what we essentially did was we scraped a lot of data from Wikipedia. So essentially, we would start at the Wikipedia article for celebrity, And then we would scrape all of the text from that article. And then for each of the linked articles on that original root celebrity Wikipedia article page, we would go to that linked page, scrape all of the text, and repeat until our depth parameter essentially reaches the base case and it stops recursively going into the linked articles. So we do that for each of these conceptual nodes. We create this data set and we train a FastX model for each of them. Then for all of the targeted interests in the IRA data, we essentially map them into one of these conceptual nodes. Then we create an auxiliary data set, which is essentially the original data, which is essentially just a spreadsheet with all of the features that I mentioned earlier with regard to the IRA data that we're interested in, except now, instead of listing out the targeted interest in just plain text, we're instead having a vector which represents the combinations of conceptual nodes that corresponds with that advertisement. And we use these features in order to train the machine learning models to perform click-through rate prediction. And then we evaluate it using conventional machine learning model evaluation approaches. So with all of that in mind, we also want to consider the optimal conceptual node combination problem, which is essentially if we have a trained machine learning model, we consider it to be a value function f, and then we have a combination of conceptual nodes, c, and then what our goal is if instead you have an allocation budget k, where should you invest your conceptual nodes? Like what combination of conceptual nodes should you instantiate in order to maximize your objective function with this budgetary constraint in mind? So this goes back to the CTR maximization problem that I mentioned at the start of the presentation. So this is essentially what we're interested in. With regard to the hardness of this problem, it entirely depends on the value function itself. So for instance, if the value function is non-convex, non-concave, then the hardness of the problem becomes NP hard simply because maximization of such functions is NP hard in and of itself. If it's linear, it is relatively straightforward, but it all just depends on the nature of the value function. So here are our proposed algorithmic solutions. We consider a genetic algorithm, which is pretty straightforward. It simply instantiates a population of children that represent our conceptual node combinations, and then we'll mutate them or randomly instantiate them over a number of generations. And for our work, we considered 1,000 generations and a population size of 35 individuals. As for our greedy algorithm, essentially what it does is it initially starts off with a vector of 0 conceptual nodes being allocated. And then it essentially performs a search where it then creates the children. It kind of considers this as like a tree search problem, where from the root, where all of the conceptual nodes being allocated are 0, it'll instantiate the children, which would be where there's 1 conceptual node being allocated for all of the conceptual nodes we're considering. And then it'll run the value function on each of the children conceptual node combinations and then choose the best one. And then it will repeat that process of simply iterating each of those conceptual node combinations and just selecting the max over and over and over again. And a good example of that is in the comment above line 12 of the greedy algorithm, where you see in the case of if you have 3 conceptual nodes that you're considering, and the vector 0, 0, 1, it would then create a set of children where each of the 3 conceptual nodes is being increased by 1. And then simply the max of those is going to be picked, and this continues until you have exhausted your budget. So now let's talk a little bit about the results. So the first thing that I want to talk about is just kind of the accuracy of this approach to conceptual, to click-through rate prediction. And what we find is, so first, we also consider 3 different cases of input. So the first case is the simplest case, case A, is essentially we only consider the combinations of conceptual nodes. We're only looking at those conceptual nodes. The second case, or case B, is we're only looking at conceptual nodes and the amount of Russian rubles that were being spent to promote the advertisement. The reason for this is because it's fairly intuitive that an advertisement that has more monetary backing is going to be pushed more heavily by the online social networking platform that it's being launched on. And then the third case that we consider are the number of days online that this advertisement is going to be, the number of Russian rubles spent, and then the conceptual node combinations. Now, again, back to my kind of the motivation of this problem, no user data is being incorporated here in terms of performing this prediction. And despite that, what we find is that these approaches do fairly well despite that very large limiting factor of not having access to user-sensitive data. This is most prominent in case C, and we see, so for instance, the y-axis in all of these plots are the predicted clicks, and the x-axis are the real click values of our training subset of the real IRA data. And what we find is that there's a positive correlation across all of these sets. And in case C, we find, it might not be immediately apparent in these plots, but we find that with the decision tree regressor and the random forest regressor, they perform the best in terms of accurately predicting click-through rates. This is more apparent in the next slide where I have a table, where I have a table featuring Pearson correlation coefficients for each of the models that we consider under all 3 of our input cases. And as I mentioned earlier, what we find is that decision tree regressor and random forest regressor in case C actually demonstrate above a 0.7 Pearson correlation coefficient with the original real click values. And I found that pretty compelling given the limited amount of data that they were used to train on. So we found that pretty reassuring and made a good case that our algorithms or our approach to performing click-through rate prediction is doing well. Next, we wanted to evaluate the performance of the algorithms in terms of coming up with conceptual node combinations that maximize expected click-through rates. And what we find is that in all cases, the genetic algorithm does close to optimal. The greedy algorithm does not, except in the case of the multi-layer perceptron neural network regressor. The reason for this is likely due to the fact that the MLP behaves more in a linear fashion compared to the others, and so the greedy algorithm was just more able to kind of capture that behavior, whereas in the other cases, it wasn't really able to pick up on that nonlinearity. And finally, in closing, one of the other things that we were interested in kind of looking at is just some overall social trends that we can observe from the data. And what we did was we simply grabbed the portion of conceptual nodes with the highest amount of clicks in the data. And then we took the average allocation of each conceptual node among this subset of the data with the highest amount of clicks. And what we found was that the conceptual nodes of celebrity, politics, and organization did notably better in terms of average allocation among the subset of high-performing advertisements than identity, news, and religion. I was surprised and also not surprised at the same time with regard to the underperformance of the news conceptual node in terms of being allocated for effective advertisements on Facebook, but I think it's interesting nonetheless. So in closing, we believe that smart advertisement is in fact possible without needing to exploit sensitive user data, and our approach demonstrates that to some degree. There is of course future work that needs to be done in order to kind of expand upon this approach to click-through rate prediction. For instance, in our approach, we consider a static data set rather than a dynamic data set in which social network data is dynamically being retrieved from a platform like Twitter. So that's an easy and intuitive way to kind of expand upon this work. But this is the first step that does show that this is in fact possible. You can perform smart advertisement without touching user data. And as I mentioned earlier, we observed that celebrity, politics, and organization were the most effective conceptual nodes in terms of maximizing clicks on online social networking platforms. And if there are any questions, I will be happy to answer them.
Yeah, hi. This is Woody Marvel.
I heard someone trying to ask a question. Could you try again and speak a little louder?
Yeah, this is Woody Marvel. I just had a question. Did you intentionally mark a categorization of the organization down into religion? Did you do that purposely to sort of get more granularity on the religious side?
A bit, and the reason for that is just because there were a lot of, in the data, there were a lot of very blatantly religious affiliated targeted interests, such as Christianity, Islam, etc., that were just very specific to religion. Whereas with organization, we were focusing more so on like groups such as the National Rifle Association, which came up a lot, or other kind of more groups or affiliations of people. And obviously one of the flaws of this approach, and something that needs to be considered in future works, is the fact that there is this possibility for overlap. So that's definitely something to think about. And our approach considers a many to one mapping. But yeah, that was part of why we had to get kind of granular there, was because if we didn't include the religion, there was a lot of overfitting that took place.
Yeah, I just was wondering if you could put something like in organization, you could have the overlap. You don't necessarily have to identify the classification of the subsets.
Yeah, that's definitely something that you could do, where, for instance, maybe like instead of African American being 100% associated with identity, maybe it could have like 80% association with it and 20% association with some other conceptual node. So maybe you could do that in order to circumvent that possibility or that problem. But for this work, we only considered like where targeted interest mapped to one conceptual node. But you're right, that's something that we could work on for the future.
Well, thank you very much.
No problem.
I have a question about the final result. Why shouldn't I put all my rubles into political advertisements, since that measured the highest?
So you definitely can. However, what we kind of found was so kind of going back to, if we look at this one, the multi-layer perceptron neural network regressor didn't really do that well. In fact, in KC, it did the worst. And that was the most, and as you can kind of see in this plot, that was the performance of that model was the most linear in nature in terms of the way that it predicted. It would essentially kind of find one conceptual node that did really well, and it would invest a lot of its budget towards that conceptual node. It wasn't exactly like that, but that's kind of what it would model to some extent. So what we find is that just with this analysis is that the mapping of that isn't really that one-to-one. So for instance, if you have 10 political conceptual nodes, people who aren't interested in politics likely aren't going to click. So you might need a little bit of culture, or you might need a little bit of identity in order to lure those people into click. So to me, it does make sense that there isn't going to be this hard linear nature to attracting clicks. So that's probably why. And our results kind of bear that out.
But the goal isn't to get the most people to click, but the most clicks total. And if you find that most clicks come from politics, then why spend any money at all on religion even though there are some people who are interested in religion and not politics.
Well, so that's definitely true, but at the same time, kind of going back to the original question, some of these things overlap. So for instance, you might have a particularly attractive topic that relates to both religion and politics. I'm sure we can all kind of imagine a case in where those two things kind of play into one another. So it kind of depends on the topic, I would guess. I don't have like a very definitive answer at the moment, but just based on these results, it does seem like there is some interplay between these things.
Other questions? What do you plan to do next?
For this work, we have talked about maybe kind of doing what I talked about earlier and maybe considering a more dynamic approach where instead of a static data set, you have a dynamic data set and you are streaming in live social network data, maybe through Twitter, because that is an option that's available, and then updating the conceptual nodes over time rather than just doing some analytics on a static data set that's never changing. So that's one thing that we've kind of kept in mind.
But you need to know the click rate of the existing, the data set you were using. You knew the click rate. How would you handle that with a Twitter feed?
But one of the benefits of Twitter is that like retweet and like rates are public. So even though we don't have click rates per se, we do have some type of measure in order to measure the reach of an advertisement.
Right. We still have a few more minutes if people would like to ask another question. Well, no more questions. I want to thank you very much, and good luck with your presentation next week at the paper. If anyone wants to send personal notes to Nathaniel, making suggestions, I'm sure he would appreciate that. One of the good things about the Keeping Current seminar is it's a low-risk way of presenting a paper before you actually have to present the paper. So thanks again, and
thank you.
Continue now. Yeah, you're welcome.